People like simple hardware stories. One chip wins, one architecture takes over, one new substrate replaces the old one. That is not what is happening underneath artificial intelligence compute. The more interesting shift is not that light is about to replace electronics. It is that the artificial intelligence chip is becoming less like a single chip and more like a system of physical compromises. Arithmetic still matters, the matrix multiply still matters, the accelerator still matters, but modern artificial intelligence systems do not only pay for arithmetic, they pay to move data, they pay to feed memory, they pay to convert signals from one physical representation into another. They pay to connect thousands of accelerators across a cluster without letting communication become the limiting layer. That is why photonics matters, not as a magic replacement for GPUs, not as a clean light beats silicon headline. Photonics matters because it is entering different layers of the compute stack at the same time, sometimes as a possible coprocessor for certain mathematical operations, and sometimes as the interconnect fabric that moves information between accelerators. Those are not the same claim. A photonic processor and a photonic interconnect solve different problems. If we collapse them into one story, we get hype. If we keep them separate, we can see the architecture change more clearly. Start with the compute layer. QANT and the Leibniz Supercomputing Center have framed photonic processors as something to evaluate under real high-performance computing and data center constraints. That matters because it moves the story out of the pure lab demonstration category. It does not prove broad superiority. It does not establish that photonic hardware is ready to displace conventional accelerators. But it does show a serious evaluation context, photonic co-processing being tested against the kinds of constraints that matter in deployed compute environments. That is useful, but only if the boundary stays visible. A company-reported workload demonstration is not an independent industry benchmark. It does not let us say that photonic processors are faster across artificial intelligence workloads. It lets us say something narrower and more valuable. Photonic hardware is being pushed toward recognizable workload classes, and the evaluation question is becoming practical enough to ask seriously. That is one layer of the story. The second layer is interconnect. NVIDIA's Spectrum-X Ethernet photonics signal points in a different direction. Here, photonics is not being presented primarily as the arithmetic engine. It is entering the communication layer, the place where accelerators, switches, and cluster-scale systems have to move enormous amounts of data reliably and efficiently. That distinction is the episode. If photonics appears in compute and photonics appears in interconnect, the conclusion is not photonic computers won. The conclusion is that artificial intelligence infrastructure is becoming heterogeneous. Different parts of the system are becoming specialized around different bottlenecks. Some bottlenecks are arithmetic bottlenecks, some are memory bottlenecks, some are signal conversion bottlenecks, some are interconnect bottlenecks, some are software and scheduling bottlenecks, where the hardware can only help if the workload can actually be mapped onto it. This is the same reason chip is becoming a less useful word by itself. A frontier artificial intelligence system is not just a processor. It is packaging, memory, networking, power delivery, cooling, optics, software, and workload orchestration. The accelerator is still central, but it is no longer the whole machine. That is why the GPU killer framing fails. It assumes that the next compute substrate has to win by replacing the previous one. But the infrastructure direction is often messier. A new substrate may win a narrow role first. It may handle a specific operation class, it may reduce one conversion cost while introducing another, it may be valuable in a cluster fabric before it is valuable as the main compute engine, it may be impressive in one workload and irrelevant in another. That is not a weak story, it is the real story. Artificial intelligence compute is moving from monolithic performance claims toward system design. The question becomes, where should the workload live? If a workload is dominated by arithmetic, conventional accelerators may still be the right tool. If a workload is dominated by memory movement, the architecture has to reduce how much data moves and how far it travels. If a workload is dominated by communication between accelerators, photonic links may matter more than photonic arithmetic. If a workload can be represented naturally in an optical system, photonic compute becomes worth testing. If it cannot, the conversion overhead may erase the advantage. That is the practical frame. not light, is better. Where does light reduce the system cost enough to matter? The literature layer helps explain why this keeps returning. Photonic neural network research has argued for years that optical systems may offer speed or power efficiency advantages for some operations in principle. But research motivation is not deployment proof. It gives us a reason to watch the field. It does not give us permission to narrate victory. The deployment proof has to come from workload-specific tests, methods, baselines, power accounting, reliability, manufacturability, integration cost, and software support. This is where the episode should be strict. A benchmark without the baseline is not a conclusion. A speed number without the workload is not a business case. An efficiency claim without conversion and memory costs is not an infrastructure thesis. A vendor roadmap is not the same thing as an independently measured production system, but strictness does not make the signal small, it makes the signal usable. The usable signal is that photonics is no longer only a distant research metaphor, it is being evaluated in compute, it is entering interconnect. It is appearing at the boundary where artificial intelligence infrastructure stops being a single accelerator story and becomes a full-stack physical systems problem. That is the shift to watch. The next generation of artificial intelligence infrastructure may not be defined by one winning chip. It may be defined by how well the system assigns each bottleneck to the substrate that can handle it. Electrons where electronics still dominates. Light where movement or representation favors optics. Memory where locality matters. And software where orchestration decides whether the hardware can be used at all. So the question is not whether photonic computing replaces the GPU. The better question is whether artificial intelligence infrastructure is becoming too large, too data hungry, and too communication heavy for any single substrate story to explain. If that is true, then photonics is not the revolution by itself. It is one sign that the revolution has become architectural. The chip is becoming a system. That also changes how we should read future announcements. When a company reports a faster optical processor, the first question is not whether the GPU is dead. The first question is, what operation was tested, what baseline was used, how much conversion was required, and where did the data live before and after the optical step? When a networking vendor moves photonics into the cluster fabric, the first question is not whether the entire data center has become photonic. The first question is, what communication problem is being reduced, at what scale, and with what trade-off in packaging, reliability, cost, and deployment complexity. When a research paper argues that an optical neural network could be more efficient in principle, the first question is not whether the future has arrived. The first question is, what operation was tested, what baseline was used, how much conversion was required, and where did the data live before and after the optical step? When a networking vendor moves photonics into the cluster fabric, the first question is not whether the entire data center has become photonic. The first question is, what communication problem is being reduced, at what scale, and with what trade-off in packaging, reliability, cost, and deployment complexity? When a research paper argues that an optical neural network could be more efficient in principle, the first question is not whether the future has arrived. The first question is, which part of the workload maps naturally onto the physics, and which part still has to be handled by electronics, memory systems, and software? That questioning discipline is what keeps the episode from becoming another hype cycle. It lets us say, yes, there is a real signal here. Photonics is moving from research vocabulary into evaluation programs, workload demonstrations, and cluster interconnect roadmaps. But it also lets us say no, that is not the same as a universal replacement claim. The mature version of this story is not a single breakthrough moment. It is a stack diagram changing over time. The arithmetic layer changes, the memory layer changes, the interconnect layer changes, the conversion boundary changes, the software layer changes, and the winning systems are the ones that make those layers cooperate instead of forcing one substrate to pretend it can do everything. And once that happens, the important competition is no longer just between processors. It is between ways of arranging physics around the bottleneck. If you found this useful, Subscribe to Quantum Convergence, AI, for more evidence-driven analysis of the systems shaping artificial intelligence.